Today's topic is exponential functions. I want you to think back to all the graphing you've done, mostly with linear equations and almost always from slope-intercept form. And what did the graph always look like? It was always a straight line, right? Well, since linear means straight line, that makes a lot of sense. However, today, we're going to look at a different kind of equation. One that you may or may not have worked with before, called exponential functions. Just a quick word, this video is going to be a little bit longer because exponential functions takes more time to explain. But we're going to jump right into our first situation. Let's say that you start out with $10, but you found a way to double your money each month. What would that look like on a graph? Let's find out. In this graph, the y-axis represents the amount of money you have in dollars, and the x-axis represents the number of months. When we have time as one of our axes, especially on the x-axis, 0 on the x-axis represents our starting time or current time. So at x equals 0, we're going to put the $10 we start with. After 1 month, we're going to double our money and we'll have $20. The next month, we double our $20 and have $40. Then $80. Then the next month, we'll be way off our graph up at $160. When we connect those dots, it's pretty obvious that this is no longer a straight line. And this type of curve is the beginning of an exponential function. What if you start with $100, but each year you lose half of the money? What would that look like on a graph? This time we have amount in dollars and number of years. Again, where x is 0, that's our current or starting time. So we're going to put our $100 there. The next year, we will have lost half of that money and we only have $50. The next year, only $25. The next year, only $12.50. And if we keep losing half of our money, right, cutting the value in half, it's going to get closer and closer and closer to 0. If you try to keep dividing a number in half again and again and again and again, you'll find that you end up getting really, really close to 0, but you never actually reach 0 itself. First of all, let's connect these dots so that we can see the shape of the graph. But then there's a definition we need today called asymptote. An asymptote is a line that an exponential function gets really, really close to, but doesn't ever actually touch. Our asymptote on this graph is at y equals 0, and that represents the x-axis. Again, it's a line we get really close to, but never touch and never cross, and every exponential function will have one. There's a format to exponential functions. The equation to an exponential function starts with the total value or ending value. That's going to equal the starting value, otherwise known as the initial value, multiplied by the rate. The rate's going to be what happens to your total each time, and the exponent on the rate is going to represent time itself. The general format is y equals a times b to the x power, where y again is your total or ending value, a represents your initial value, b is your rate, and x is time. Just remember that b is the only value that gets taken to the power. Our money situation, our last money situation then, would be y equals 100 times 1/2 to the x power, where again x is the number of years and y is your current amount of money. Let's take a look at writing an equation, an exponential equation from context, and solving. Let's say that we have a population of mice, and that population quadruples every 6 months. If a mouse nest started out with only 2 mice, how many mice would there be after 2 years? We're going to write an equation and then use that equation to solve the problem. The very first thing you need to do is read through the scenario carefully. I'd recommend reading it twice and identify your known quantities. In this case, we have a starting value of only 2 mice. What's happening to those mice is they're quadrupling, right, or being multiplied by 4. And the time, or how many times this has happened in this scenario, every 6 months for 2 years, means that this population has quadrupled 4 different times. What is it that we want to know, or what is the problem asking for? The total number of mice after 2 years. Let's put that into our exponential equation. Again, remember we have total, beginning value, rate, and time. In this case, it's going to be y equals 2 times 4 to the 4th power. We started with 2 mice. They're getting multiplied, or the population gets multiplied by 4, and it's happened 4 different times. Now we need to use order of operations to solve this equation. In order of operations, exponents have to come before multiplication. So the first thing I do is multiply 4 to the 4th power. That gives me 256. Then I can multiply the value by 2 and I get 512. Now 512, we're almost done, but just saying the number 512 doesn't mean a lot according to our situation. So the last thing you need to do in context problems is interpret the solution in terms of the context. What I mean by that is explain your answer. In this case, 512 means that there will be 512 mice after 2 years. In situation number 2, we have a sporting tournament. Think March Madness. Teams are eliminated after they lose a game. The number of teams in the tournament decreases by half with each round. If there are 16 teams left after 3 rounds, how many teams would have started out in this particular tournament? Again, it's important to identify what you know. We know that our ending value, right, after 3 rounds we have 16 teams. We've had 3 rounds that have already happened, and our rate is 1/2 because 1/2 of the teams are eliminated each round. What it's asking for, or what we don't know, is how many teams the tournament started with, or the initial value. So let's take our exponential equation and plug in our values. We have 16 teams left equals the beginning number of teams multiplied by 1/2 to the 3rd power, because our teams again half are eliminated each round, and we've been through 3 rounds. To make this a little easier to solve, I've changed 1/2 into 0.5, and 0.5 to the 3rd power is 0.125. Now I can't multiply 0.125 to an unknown value. Remember, a is what we're solving for. So to get a alone, or to isolate a, I have to divide both sides by 0.125. And I get a is equal to 128. What does that mean to our situation? It means that there were 128 teams that started out in the tournament. We know that these situations are exponential functions because instead of increasing or decreasing by the exact same amount each time, we're increasing or decreasing by a rate. Things like doubling or getting cut in half. Those are situations that require exponential functions. Now, we're going to talk about a special kind of exponential function where the rate of increase or decrease is a percent. That's going to be a little bit different than just doubling or getting cut in half. We still need to identify what we know. We're talking about the population of a small town that's increasing at a rate of 4% per year. If there's currently 6,000 residents, we want to find out how many residents will be there in 5 years. Well, we know that we started with a population of 6,000 people. This population is growing by 4%. And 5 periods will have passed when we want to know the population. We want to be careful with the percent. That's the part that's different in this scenario than the others. We want to know the total population after 5 years, and when I plug these values into my exponential equation, most of it's pretty straightforward. I want to know the total. I started with 6,000, and it's 5 years that we want to calculate the population for. What's different though is take a look at my rate. 4% as a decimal is 0.04. But if I put 0.04 in as my increase rate, that's only going to tell me 4% of the population. When your rate is a percent, we have to include the 4% increase on top of the 100% of the population that was already there. So in a growth or decay equation, we have to add 100% to our growth rate. 104% is the population growth. So 1.04 is going to be my rate. 1.04 to the 5th power gives me a big long decimal that I don't want to round. I'm going to caution you against rounding decimals until you're done with the problem. So leave that number on your calculator screen when you do the calculation, then multiply it by 6,000, and you should get 7,299.917 with a big long decimal afterward. What's wrong with this answer? What happens when we go and explain our situation this time? Can I have a population of 7,299.917,414? Absolutely not. I can't have partial people. So when you explain your answer, don't forget to look at the context. In this case, I'm going to round to the nearest whole person. And when I interpret my solution, say, there will be about 7,300 people in this town in 5 years. One more example, because we need to look at a situation where we're reducing or decreasing by a percent. Let's say we want to reduce the size of a picture to place it in a small frame. We're going to use a photocopier to do that, but you're not sure what size to choose on the photocopier, so you decide to reduce the picture by 15% each time you scan until you get the size you want. If the picture was 10 inches long at the start, how long will it be after 3 scans? Again, let's write down what we know. We know that the starting length of the picture was 10 inches. We're decreasing by 15% each time, And when we want our answer, we will have decreased the size 3 times. So 3 is going to be our time. We want to know the final size of the picture after 3 scans. When we put our values into our equation, most of it's pretty straightforward. We want to know the total after 3 scans. There are 3 scans, and we started with a 10-inch long picture. It's the rate that gets tricky when it's a percent. If I'm decreasing by 15% each time, after I decrease by 15%, I actually have 85% of the size left over. 100% decreasing by 15% each time leaves me with 85%, and it's the 85% written as a decimal that I would put in as my rate. Solving requires order of operations. 0.85 to the third power gives me 0.614125. Multiply that by 10, and I get 6.14125. When I explain my solution, I'm going to say that the picture will be about 6.14 inches long after 3 scans. Okay, I know that that's long. Just a quick review of percents of increase or decrease. Remember to write your percents as decimals, and if you have a growth rate, add it to 100%. If you're decreasing or you have a decay rate, subtract it from 100%, and what's left over will be the rate to put in your exponential equation. As a side note, remember doubling means multiply by 2, tripling multiply by 3, quadrupling multiply by 4. If something gets cut in half, use 1/2 as your rate, and if something gets cut into a third, remember to use a third as your rate, and so on and so forth. All right, thank you for your patience. I'm going to end by wishing you a great day, and I will see you next time.